All right, ladies and gentlemen, welcome back to section 4.5, day 1. Today we're talking about two big topics today, linearization and differentials. Okay, so we're going to tackle each of these separately, and we're going to start with what I think is the easier of the two, which is linearization. So that's kind of a fancy schmancy sounding word, but all a linearization really is finding the equation of a tangent line. Okay, now we're going to have a slightly different formula for this. But really, you're kind of just going to go through the same steps you normally would, right? If I gave you a function and an x value, how would you find the equation of that tangent line? That's basically what we're going to do here. So let's start with the little formula though. If f of x is differentiable at x equals a, then the equation of the tangent line is L of x. So you'll see that this function is called L of x, right? L, because this is standing in for the linearization, right? So L of x is going to equal f of a plus f prime of a times x minus a, where x equals a is the center of approximation. So that's a fancy little phrase there. All that really means is that's where we're finding the equation of the tangent line. So at some x value, which we'll call a, we're going to make the tangent line there, okay? And so you're going to look at this and you're going to go, this looks a little weird, right? But actually, you've seen something like this before. The format of this L of x equation is actually the same thing as point slope form, just with the y1 subtracted over to the other side. So here's what I mean. Y equals y1 plus m times x minus x1. So if you kind of line up the pieces here, right, you'll see kind of how everything makes sense. Normally when we look at point slope form, that y1 is over on the left-hand side. But y1 and x1, right, are the point, right? The point where you're saying that this line goes through, right? Which in this case makes sense. That's going to be my point of tangency. F prime of a is the slope of my tangent line at x equals a. Okay, so this is the formula we're going to be using, all right? And again, it is going to be based off of the slope-intercept form. So if you ever forget this formula, did I say slope-intercept? I'm sorry, I meant point-slope form. If you ever forget this formula, just think point-slope form and you're solving for the y. So you got to move the y1 over, okay? Okay, so linearization is just, again, the equation of a tangent line, slightly rewritten from what we're used to with point-slope form, okay? So here's what we're going to do with it, okay? Let's take a look at an example, because what we're going to do with the equation of the tangent line is going to be a little bit different here. So we have a function f of x, okay, and we have 2 points on this function. So the first point is going to be the point at x equals a, where we are going to make our tangent line, okay? So I'm going to go ahead and do that, all right? At a comma f of a, I'm going to make my tangent line, and it's going to look something like this, okay? Maybe do that arrow. There we go. Okay, so there's my tangent line, my blue tangent line right there at x equals a. And now, what we're going to do with the tangent line is we're going to use the tangent line to approximate other values of f of x. So if I have some other point on my function here, so that's going to be my orange point here, right? Instead of plugging that x value into the function, what I can do is I can plug that x value into the tangent line I made at x equals a, and I can evaluate it on that line, and I can go ahead and get an approximation for the value of the function. So what we're saying here is that I am taking some x value that normally I would plug into f of x. But instead, I'm going to plug it into the nearby tangent line. And what that's going to tell me is that f of x is going to be approximated by my tangent line. F of x is going to be approximated by my linearization. Okay, so again, we made this tangent line at x equals a. And now for some other x value that's close by, what we're going to see is, right, that the value of the function there is going to be very similar and close to the value we would get if we were to plug x into the equation of that tangent line, aka the linearization at that nearby x value. Okay, so we're going to see this in action, all right? And so here's how these questions are going to go. These are going to go in two parts, okay? So example 1 says, find the linearization of f of x equals cosine of x at x equals pi over 2. I'm going to stop reading right there because this right here is going to be the first part of this question. Find the linearization, right? Okay, so that right there just means find the tangent line. You have a function, you have an x value. This is something we should be able to do, okay? So first thing I need is a point, right? So I'm going to plug pi over 2 into my function, right? So cosine of pi over 2 is going to be 0, okay? So that's going to be my y coordinate. I'll come back to that. Now I need a derivative. So f prime of x, what's the derivative of cosine? It is negative sine of x. And now I need the derivative at pi over 2. So f prime of pi over 2 is negative sine of pi over 2, which is going to be negative 1. And now I have a slope. So when x is pi over 2, I have a y of 0, and I have a slope of negative 1, right? And so I'm going to write this out, okay? And, if you want to think of this like, if you want to write this in point slope form first, you can, right? I'm actually not going to. I'm going to go straight to the linearization formula, right? L of x equals, so f of a is just the y coordinate here, which is 0, plus my slope, which is negative 1, times x minus my a value, which is pi over 2. Okay, and so the 0 is going to go away, and so I'm going to get just negative 1 times x minus pi over 2. And to be honest, if I asked you on a quiz or a test, you could leave it like this as well. You don't have to distribute and combine the like terms. That's okay. Okay, really anything like this will do just fine. Okay, so that's the first part of this question, right? We're just finding the equation of the tangent line at pi over 2. Now here's the second part. This is the interesting part. Use it to approximate cosine of 1.75 without a calculator. And this is where linearization becomes a little bit interesting, right? Instead of just finding the equation of the tangent line and then not doing anything with it, right? This is an application of not just derivatives, but specifically the equation of the tangent line. I want you to think back, right? In the time of Isaac Newton and Leibniz, when these guys were thinking of the concepts of calculus separately in England and Germany respectively, right? There were no calculators, right? So if you wanted to know something like the cosine of 1.75, how could you do that, right? Well, what we can do and what they did is you can make a tangent line at a nearby x value. Remember, pi over 2 is about 1.57, right? So 1.75, not that far away, okay? And so, cosine of pi over 2, that's easy, right? That's a unit circle value. But cosine of 1.75 without a calculator, that's kind of tough to do, okay? Now, lucky for us, we live in a world where we do have calculators, right? So here's what I want to do. I want to cheat, okay? I'm going to go ahead, and I think I've already done this on Desmos. Yep. Cosine of 1.75 radians is negative 0.178. We'll round to 3 decimal places, okay? So cosine of 1.75 is approximately negative 0.178 using our modern technology and our calculators. Okay. But what I'm going to do now is let's see what my approximation would have been like if this was in the, 18th century, right? In the time of, post-discovery of calculus, okay? So what would L of 1.75 be? If I take 1.75 and plug it into the equation of the tangent line we got from the nearby pi over 2, what would I get? Well, that would give me negative 1 times 1.75 minus pi over 2. And so if I distribute that, that would give me negative 1.75 plus pi over 2. Okay, so this is my kind of exact it feels weird to say exact approximation, but that's exactly what this is, right? This is going to be my approximation for cosine of 1.75 done, 18th century style, okay? So let's see how good of an approximation this actually was. So again, we have calculators, so we can go ahead and do that. So I'm going to go back to Desmos now, and let's figure out what this would be as a decimal, and we can actually see how good of an approximation this is, okay? So let's go ahead and do negative 1.75 plus pi divided by 2, and we get negative 0.179. Holy crap, that's a pretty good approximation. This is approximately negative 0.179. So look at this, right? Look at what we are able to do here, okay? Right? By using the equation of a nearby tangent line, right, we came up with an approximation for cosine of 1.75 that's just 1/1000th off, okay? And this approximation, again, this is my exact approximation, negative 1.75 plus pi over 2. This is all using skills that were available literally hundreds of years ago, right? We can come within 1/1000th of some, kind of random irrational number, right? And all we did was we found a nearby tangent line, right? At A in our example is pi over 2, right? And we took some other x value, plugged it into the tangent line we got from that, right? And we were able to come up with a pretty good approximation that's just 1/1000th off of the actual answer, right? That's pretty impressive, okay? So that's what we're looking at here, right? So this is an application of tangent lines, right? Kind of back when calculus concepts were first being discovered and talked about, okay? So let's do another one. Okay, example 2. Find the linearization of f of x equals root 1 plus x at x equals 0. Full stop right there for a second. Okay, let's do that first. That just means find the equation of the tangent line. So the first thing I'm going to do is get my point. So let's plug 0 in. So f of 0 is the square root of 1 plus 0, which is the square root of 1, which is just 1. So that one's easy. F prime of x, we need a derivative. Technically, this is chain rule, right? But 1 plus x's derivative is going to be just 1, so I can kind of ignore it, right? What's the derivative of a radical? You can go power rule, 1/2 radical or x to the negative 1/2 or 1 over 2 root x. I'm going to go with the latter, 1 over 2 root, not just x though, right, 1 plus x. And again, this is technically a chain rule, but what's the derivative of 1 plus x? It's a 1, so I'm going to ignore it. Okay, and now f prime of 0, right, if I plug 0 into this, right, I'm going to get root 1 again, which is 1 times 1/2. I'm going to get just 1/2. Okay, so what's the equation of my tangent line, right? What's my linearization? L of x equals f of a, which is 1, plus the slope, which is 1/2, times x minus a. And I'm going to go ahead and simplify this and distribute. I'll get 1 plus 1/2 x. Okay, so that's the first part of the question, right? This is something we should all be able to do. Find the equation of the tangent line, right? If you're writing it in point slope form, you're getting the y by itself, right? And you're just replacing it with this function named L of x. Okay, now let's see what we're asked to do. Use it to approximate the square root of 1.02 without a calculator. Well, again, we live in a calculator world, so I'm going to go ahead and cheat. Let's go back to Desmos, and we will cheat here a little bit. Square root of 1.02, 1.00995. Okay, so I'm going to write a few more decimal places here. 1.00995. So this is the answer we get, right, using a calculator, being cheats, okay, or using a calculator, I should say, right, being cheats here, okay. But how would I have done this without a calculator? Well, what did we do? We found the equation of a tangent line at x equals 0. But here's the thing, right, and something that's going to make this question a little bit different, right, is that I don't want x here to be 1.02. And this is a common mistake people make with linearization questions, right? They look at this and they go, okay, just whatever I'm trying to approximate should be the x value, right? Well, not quite. You want to consider what the function is, right? If my function was the square root of x, then absolutely x would be 1.02. But here the function is root 1 plus x, right? So in this case, x only has to be 0.02, right? If x is 0.02, also think about that is closer to 0 than 1.02 would be, right? 0.02 was x, that would give me the square root of 1.02 when evaluating my original function. Okay, so this one's a little bit trickier, right? So L of 0.02, right, means go ahead and plug that into the equation of the tangent line we just found. So we get 1 plus 1/2 of 0.02. So we get 1 plus 0.01. And so I get, again, it's a weird phrase, my exact approximate, right, to be 1.01. Compare that to what we get from the calculator, 1.00995, right? And you may think these are really far off, but actually they're, again, less than 1,000th off, right, of each other. So again, a pretty good approximation considering I could have done this in a time where, you know, electricity wasn't around. Okay. Okay, so that's all we're going to talk about with linearization, all right? So now we're going to switch gears and we're going to scroll down and we're going to talk about differentials, okay? So a differential, the first thing I want to talk about with the differential is what is a differential, okay? And so I'm actually going to jump down here a little bit, okay? And we're going to get to all of this, all right? Don't worry. But let's talk about f prime of x real quick, okay? So f prime of x we can also rewrite as dy dx, okay? right? And sometimes when we write an answer, we write, dy dx equals blah, 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 right? But technically, this is a fraction, right? Dy is divided by dx. And we don't really think of those as being separate. We kind of think of it as one term. But actually, those are my two differentials for those variables, dy and dx. Okay, so that's what a differential is, okay, right, is dy and dx, and you can do this for any other variable that you're using, okay, but what does it actually represent, okay? So the d notation here is based on delta notation from slope, right? So let's go back to a good old slope formula, right? Well, what is slope? How do we calculate it, right? Rise over run, change in y over change in x, or delta y over delta x, okay? If you pick 2 points on a function, right, you can calculate the exact change in y and change in x, okay? Differentials are going to approximate those, okay? So we're going to come back to this idea once we take a look at the picture to the right there, okay? I want to stick with the good old slope formula for a second here, okay? M equals delta y over delta x. Well, what can I do with this formula? Well, one thing I can do is I can solve for this delta y term, okay? I want to isolate this term right here, and so I'm going to get delta y equals, and so I'm going to multiply delta x over to the other side, okay? So if I tell you the slope of a line and I tell you the difference in the 2x values on that line, you can calculate the exact change in the y values by using this formula. Now, we wouldn't really think of doing it this way, right? We'd plug the 2x's into the function and subtract, right? But you could do it this way, right? This is taking good old classic slope formula and just kind of rearranging it. Okay, and so if I go over to this picture here, which looks pretty complicated, okay, but what I'm going to do is I'm going to pick out 2 points on this. So this kind of bluish, tealish curve here has 2 points on here I want to spotlight. Point P right there, and this one is point Q, okay? And if I take the y values and subtract it for each of those, I can get delta y. Okay, so again, that's one way of getting delta y. Another way, though, is by rearranging the slope formula, m times delta x, right? I can also subtract the difference in the x values, and I can figure that out as well. Okay, so here's what we're going to do. Okay, we can do this same idea with the slope, okay? F prime of x we can consider to be dy dx, right? And now what I'm going to do is I'm going to solve for the differential dy. So dy is going to be f prime of x times dx. Okay, and now this is the formula that we're going to be using in this section. But again, I want to show you what we're going to be using this for and what this means graphically. Okay, what dy is going to represent is if you pick some x value to start with. So again, my first point here I picked was p, right? And now I'm going to go delta x units over. Now, lucky for us, delta x is going to be the same thing as dx. Those are going to be the same value because you always have to know what the change in x is. So, you're going to start at an x value. You're always going to know what the change is, okay? So delta x is going to mean the same thing as dx. But what we're doing here is we're multiplying delta x by the slope of a tangent line, right? Whereas in classic slope formula, that's the slope of a secant line, okay? And so multiplying by the slope of a tangent line is going to give us an approximation for the change in the y values. Delta y is going to be approximated by the differential dy. Okay, these are approximations of each other. All right. So again, what we're kind of talking about here is what could we have done with a tangent line before we had electricity? What was an application of a derivative, of finding a tangent line, right? And one thing you can do is you can approximate the change in the y value without actually having to calculate two y values and subtracting them. Okay, so that's exactly what we're going to look at here. All right, so example 1 says find the differential dy. So again, I'm going to do a full stop here, right? I'm not going to read anything past this. We have a function y equals x to the fifth plus 37x. Okay, and so what I'm going to do now, right, is I'm going to find the differential dy. I'm going to take this equation, I'm going to take the derivative with respect to x, okay? So the derivative of y is going to be dy dx, and on the right-hand side, I can just use power rule, so I get 5x to the fourth plus 37, okay? And now I'm going to go ahead and multiply the dx over, right? Normally, we're so used to just stopping there, right? But what I'm going to do is I'm going to multiply the dx over, so I get 5x to the fourth plus 37, that quantity times dx. So this is the formula to calculate the differential dy, okay? And now what I'm going to do is I'm going to evaluate dy for the given values of x and dx. Okay, so another way of thinking about this, right, is that dy is like y prime times dx. Okay, now I'm doing this in another color, but again, these mean the same thing, right? This time around, I'm just going to do this at a specific x value. So what this is saying is if I start at x equals 1, right, dx is 0.01, that means it's going to get bigger, right? So start at 1, go to the right 0.01 units. What is the approximate change in the y values? Okay, that's what we're going to calculate with this formula. So dy is going to be 5 times 1 to the fourth plus 37 times the change in the x values, which is 0.01. So 1 to the fourth is just 1, times 5 is 5, plus 37, I get 42 times 0.01, and when I multiply these out, I get 0.42, which tells me that if for this function, if I start at 1 and I go to the right 0.01, the y is going to get bigger by approximately 0.42. Okay. Again, I could actually plug these into the function, right? And I could calculate what the delta y could be, right? But I think this is actually faster, right? Do you really want to take 1.01 to the fifth power? Do you want to sit there and do that? I don't think so, right? Again, you have to think about this as one of the early applications of what we could do with a derivative, right? Again, no electricity times, no calculators, right? None of that. Okay, and we can get an approximation here, all right? Now, again, I want to show you, right, is this a good approximation? So let's actually go ahead and calculate the actual delta y, and let's see how good of an approximation we did. So I'm going to go back to my old friend Desmos here, and I'm going to type in our function f of x equals x to the fifth plus 37x. And now, what if I actually subtracted those x values? F of 1.01 minus f of 1. Okay, again, dx is delta x, right? So that's 0.01. That's the difference between the two x values I'm plugging into the function. And what is that difference? It's 0.421, right? So again, we're off by a little bit more than just 1/1000th, right? Doing this approximation, I could have done, again, back in the 18th century. I can't get over that, how good of an approximation this really is. Okay. Okay, let's do another one. Let's look at B. Okay. Y equals sine of 3x. So first thing I'm going to do is I'm going to find the differential dy. So I'm going to take my equation. I'm going to take the derivative with respect to x. Okay. So what is the derivative of y? It is going to be dy dx. Remember, that's implicit differentiation, right? That's section, when was implicit differentiation? I want to say section 3.7 that was. Okay. And now, right-hand side, sine of 3x, we have to use chain rule. So we're going to get cosine of 3x. And we're going to multiply this by 3. And so we're going to get dy dx equals 3 cosine of 3x. But, oh, whoops, I remember. I'm trying to solve for the differential, right? Okay, sorry. So we did that up here. Let's multiply the dx over. My bad. So we get dy equals 3 cosine 3x times dx. Okay? So now let's calculate this differential at x equals pi. And what we're saying is, starting at pi, if x is going to go to the left 0.02 units, right? Negative 0.02. If we go to the left on the x-axis from pi by 0.02 units, what would the approximate change in the y values be? So let's plug it in. So we're going to get 3 cosine of 3 pi. And we're going to multiply this by negative 0.02. And so cosine of 3 pi is coterminal with pi. So this is going to be 3 times the cosine of pi, which is negative 1 times negative 0.02. So double negatives, I'm going to get positive, right? So 3 times 0.02 is going to be 0.06. Okay, and that's going to be my approximate change in the y values. Again, let's see, right? I'm doing this 18th century, right? How good of an approximation is this? All right, let's check this out. So let's go back to Desmos. I'm going to change my function here to be sine of 3x. Okay, and so let's do f of... And so this is going to be kind of weird, but let's go pi minus 0.02. And from that, we will subtract f of pi. Okay, and so what is my difference? It is 0.059964, which if we were to round would be 0.06, right? So again, another extremely close approximation for the correct delta y, which we are doing here. Okay. Okay, one more differential I want to calculate. Now, this last one for C, I already have everything written out here. So if you want to pause it after I'm done explaining and copy it down, that would be great. Okay, but I'm going to show you this one actually in 2 separate ways. Okay, so let's take a look at x plus y equals xy. All right, so we're going to first find the differential dy, and then we will plug in our x value of 2, and we're going to say we're moving to the right, 0.05. So what's the approximate change in the y values? Okay, so I'm going to show you this twice because a few years ago, a student of mine gave me a totally different way of doing this, which is just as valid. So I want to make sure that you all see that second way as well. Okay, so here's the first way. All right, let's just do what we did last time. Let's take the derivative right away. But now we have multiple y terms here, right? So this is why I brought up implicit differentiation, because you can absolutely use that here, right? So derivative of x is 1. derivative of y is dy dx, and on the right-hand side here, right, how would you take the derivative of xy? Well, you would have to use the product rule, right? So x times the derivative of y, which is dy dx, plus y times the derivative of x, which is 1. And now I have multiple dy dx terms, so I bring them all to one side, factor it out. Anything that doesn't have a dy dx goes on the other side, okay? And now I divide, and so I get dy dx equals y minus 1 divided by 1 minus x. And then I multiply dx over to get my differential. Okay, so nothing super crazy here. You've all done implicit differentiation before, but what makes this difference, and this is something similar to back when we were looking at questions that were just on implicit differentiation, is in order to actually calculate the differential dy, I need to know the x and the y coordinate at my x value, right, which was 2. So I need to find y when x is 2. So I'm going to take 2 and I'm going to plug it back into the original equation. Okay, so if I take this 2 here, right, plug it in for x, plug it in for x, what y value do I get, right? And so you can solve a little equation there, and you're going to get that y is also 2. Okay, so now I know x is 2, I know y is 2. Now we can plug everything in and calculate our differential dy, and we get negative 0.05. Okay, so this is how my brain initially thought of doing it, but a few years ago, a student of mine said, why are we taking the derivative right away, right? When you can take this equation, right? And what if we were to solve for the y terms? Okay, so if I subtract the y over to the right and factor it out, now I can divide, and I get y equals x divided by x minus 1. And this takes care of the need of having to figure out what the y coordinate's going to be when x is 2, right? Because now when I take the derivative, I'm going to have dy dx equals, on the other side, I just do quotient rule. All of those terms have x's in it. Now, the one downside of doing it this way is you got to do the quotient rule, which personally not a fan of, but hey, it works. Okay, so you can isolate the differential dy by multiplying the dx over after you do your quotient rule. And now you can plug in x is 2, dx is 0.05, and evaluate it, and you're going to get the same answer. Okay, so it's really just a matter of personal preference here as to what you want, but you can do this either way, and you're still going to get the same differential dy. Okay? All right, so that's all we have for today. I will see you next time.